Okay, thank you for the invitation and for the introductions. It's my honor to give a talk here. Okay, this talk is about the K-moduli space of the Pezzo surface pairs. This is my joint work with my two collaborators, Pan Long and Haoyu. Okay, this moduli space is related to the moduli space of K3 surfaces. So let's give some background about the K3 surfaces. In this talk, we work over the complex number field. A K3 surface is just a project surface with the irregularity is 0 and its canonical bundle is trivial. K3 surface with additional structures are usually related to some follow geometries. In this talk, we will focus on two examples. The first one is we view K3 surfaces as anti-canonical sections of follow threefolds. For example, if we consider a prime follow threefold, so its anti-canonical sections is a multiple of some n-pole line bundle. So we can take general anti-canonical sections. Then we will get a polarized K3 surface of fixed degree. This degree is just these intersection numbers. So it's 2G minus 2. Here, G can be viewed as the genus of the in these sections, in this polarization. A larger example we focus will be the K3 surface comes from the Pezzo surface. So if you consider a Pezzo surface of degree D, then you can consider the double cover S of this Pezzo surface branched along a curve C lives in this linear system. Then you will see that S is a K3 surface. But additionally, you will get another structure on this K3 surface. That is an involution. Tau maps to S. This just switch the double covering. So you will get this additional structure as an anti-symplectic involution. Here, anti-symplectic involution means that you maps the holomorphic two forms on K3 surface to its minus anti-canonical minus global holomorphic symplectic form. Okay, so you will see that these are two typical examples of K3 surface with additional structure. They are related to follow geometry. So we care about the moduli space of this K3 surface with special structures. Then it will has many different kinds of compactifications. These different compactifications from different perspectives. For example, we may have a geometrical invariant theoretical compactification that is known as GIT compactification. For example, if we consider the first kind of K3 surface in the last slide. See here, the K3 surface in its anti-canonical system. Then you will naturally have some GIT compactifications for this moduli space. Another compactification is from Hodge theoretical side. A well-known theorem on K3 theory is that the Euler theorem. It says that we can recover a K3 surface via its integral Hodge structure. So if we consider a lattice of signature 2n that is given by the integral Hodge structure of K3 surface, and you will get a paired domain defined by this lattice. Then you may consider that the Morjomi groups of these K3 surfaces with additional structures. Then you can take this quotient. This quotient is known as locally symmetrical varieties. As this locally symmetrical variety is a orthogonal type Hermitian domains. So it has well-known compactifications known as Baily Borel compactifications from arithmetic side, because in this case this locally symmetrical variety will be the complex point of so-called Schmer variety. So they have some compactifications from some arithmetic side. This is Baily Borel compactification. They can be compactified and some approach of some automorphic forms on this locally symmetrical space. So this is why we call it arithmetic. For example, if we consider the polarized K3 surface, then its lattice will look like this. Yeah. Then you will get this Baily Borel compactification. Actually, we have another compactification. This is related to our today's topic, that is K-moduli side. This means that we can view this pair. Here X is just a follow variety, or in our concrete example is follow threefold, and S is just anti-canonical section in this follow threefold. Then we enter a coefficient C here to ensure this is log follow pairs. Then you may consider the K-moduli compactification for these pairs. If X has no deformation, say it is rigid, then so the whole moduli will appears on the K3 side. So this will give you some compactifications for the model space of K3 surface. So the question we are care about is such question: how do we compactify these compactifications for our model space of K3 surface with additional structures? Actually, this question is asked by Xu in his survey articles for the model space of primitive follow threefolds. This is just the examples in our first examples in the first slide. Maybe we can return back later. Here, in this case, the follow threefold is prime follow threefold. Okay. So the model space of K3 is just quasi polarized model space of quasi polarized K3 surface. This. So this question is also can be asked for any follow geometries related to some K3 surface with additional structures, not necessarily view K3 as anti-canonical section, but also like viewed as a double cover of some follow surface. That is the pale surface. Actually, there is a general expectation for these questions. A general expectation is just we hope that K-moduli wall crossings will give an explicit resolution of these two compactifications, because in this case we have natural paired map that is you can divide for example in the smooth knockers that you can associate a paired point to it for the smooth K3 surface, or for smooth object you can associate a paired point that lives in these compactifications. So the Taylor theorem says this is a biracial map. So the general expectation is that the K-moduli wall crossings will give an explicit resolution of this map. Okay, let's see some examples that we have known. The first example that we have learned is that for G equal to 2 case, that is the moduli space of quasi-porous K3 surface of degree 2 or genus 2. In this case, a general K3 surface can be viewed as a double cover of P2 branch along sextic curves. So you may view such K3 surface as a log de Pezzo pairs, that is P2 plus a curve with some coefficient in this curve. Then you make it a log follow pairs. Then you can use the K stability to compactify this model space. Then you consider the wall crossing behavior. This wall crossing will give you the explicit resolution of this biracial map. Actually, for the second example is the double cover of P1 plus P1 branch along by degree 4 curve. Actually, this is degree 8 de Pezzo surface. Then you first you have some GIT compactifications for this space, and this pure map can be explicitly resolved by the work of Ascher, DeVleming, New in 2019. Actually, their proof is based on some works of Laza agreed in 2018, I think. They can actually identify the K-moduli space of pairs to some variation of GIT space. For the variation of GIT space, Laza and Algebraic has already proved VGIT can resolve this paired map. So their work is just to identify the VGIT and the K-moduli space. The last example we have learned is the the cortical surface case. For the cortical surface case, there is no VGIT, but luckily that Laza and Algebraic, they give a prediction of these explicit biracial maps. Then Ascher, DeVleming, New in 2022, they verify their conjectures via the K stability theory. So these are almost the examples we have learned so far. In today's talk, we will focus on another example, that is double cover of Hodge surface F1, or we always identify it as a blob of P2 at 1 point. So let's move to the K-stability theories. Let's recall that log-follow pairs is called K-semi-stable. If it satisfies this evaluative criteria, it says that the beta invariant of these pairs is always non-negative for any prime divisors over X. Of course, this is not the original definition of K-semi-stability using the test configurations. But in practice, especially in some examples, this criteria is much effective to detect K-stabilities for the test configuration. So we just use this definition. If this log-follow pairs is so-called of complexity 1, then there is a much more effective criterion to detect their K-stability. This is due to the work of Zhuang and Susis and many authors in their work on Calabi problem for follow-through folds. Yeah. So in this talk, we focus on the surface case. So I just stated this theorem in dimension 2. This theorem holds in general case. So let this XD be a two-dimensional log-follow pairs. The complexity 1 condition means that you have an effective action of one-dimensional torus. Then the equivalent K-stability says that equivalent K-stability criteria says that if you want to check this pair is K-polystable, you only need to check these particular divisor valuations. The first is so-called the vertical prime divisors. That is the orbit under this torus action is one-dimensional. The second is that the beta invariant for the horizontal invariant prime divisors is vanished for this divisor. Their beta invariant will be vanishing. The third is that the Futaki character will be vanished for the one-parameter subgroup in this torus. In this case, the Futaki character is also the valuation induced by this one-parameter subgroup or this one-dimensional torus. Now we stated the moduli theory for this log-follow pairs. So you consider the moduli stack of K semi-stable pairs of log-follow pairs. In this talk, we focused on this special case. That is, we require X is of Q-follow varieties, and the boundary D is lives in some multiple of anti-canonical sections. For simplicity, in this talk, we consider M is equal to 2. Then the moduli stack of such pairs, K semi-stable such pairs, will admit so-called good moduli space. So this good moduli space will parameterize the K-polystable pairs. The more interesting things for this talk is that if we vary this coefficient in these pairs, the moduli space will have so-called wall crossing behaviors. This is proved by Ascher, Keel, and DeVleming and Neil in 2019. So let's recall their results. Their results says that there are finite many of rational numbers. That is, we call the walls, W1 and W2 and Wm, such that if you let the coefficient C in the same interval, same interval, then this moduli space is isomorphic. Actually, they have natural isomorphic. They have natural isomorphism. So we can we can define this space for C in the same interval. Then, if you let C across this number Wi, then there is a so-called wall crossing behavior. That is, there is a finite maps for this moduli space. So you may contract some C here to here, and also contract some C from here to here. More importantly for us, that if you look at the local behavior of this wall crossing, there is a general framework called the local VGAT theory. Actually, they prove that this wall crossing is just the local VGAT theory. Now we turn to the Hodge theoretical side more explicitly in our example. So if you consider the double cover of our dipole surface of degree 8, then you can compute its layer group very explicitly. So generically, we have its layer group look like this. Here, L you can be viewed as the pore bank of the O1 on P2. The E is just the exceptional. They come from the exceptional divisors of blob P2. So you can consider its transcendental lattice of this layer group. Then you can easily compute it. This lattice is just two copy of U2, that is hyperbolic lattice, and then E8 lattice, E7 lattice, and A1 lattice. Then we can define the paired domain like this, and the paired domain has two correlate components. Here, plus means you take a correlate component of this space, and in this case we can take a Morjomi group as the orthogonal group, so-called. That is, you preserve this the intersection forms on this lattice. Pair plus means you preserve the component. Maybe I want to remark that here we do not need to take the so-called stable orthogonal group, because here the moduli space is come from the double covering, so it's not the moduli space of quasi-polarized or moduli space of lattice polarized K3. So the Morjomi group is a little different from the quasi-polarized case. So now we can consider the quotient space for this, since this group can naturally act on this paired domain. Then you can easily compute this is an 18-dimensional space, since this lattice has signature 218. Sorry. Then the Baily-Borel compactification for this space is just some curves and some points. because the boundary of the Baily-Borel compactification is determined by some isotropic subspace in this lattice, but you need to base change to the rational coefficient. That is rational vector space. So your boundary dimension has smaller than 1. Okay. So if we consider the moduli space of these pairs, it will not be a proper space. So the machinery we discussed before will provide some severe compactifications. The first one is that we will have a GAT compactification for this space P, but we need to modify this GAT compactification because the automorphism group of F1 is not a reductive group. So if you take a naive quotient, you will get a so-called non-reductive GIT. So yeah, you need to use some works of like Curwen's work. But in this explicit case, we can construct a GIT reduction. The idea is very simple, actually. If you view this curve as the curve come from the P2, then the curve on P2 will be a plane sextive curve. It will look like this if you take the blow up of P2 and to 0.100. So you will see that this curve D has a multiplicity 2 and the 0.100. So we need to assume that F2 has generically rank 2, then this curve will have this normal form. Actually, this normal form is just obtained by Q out of the the unipolar part of the automorphism group of F1. So after the unipolar part of automorphism group of P1, then you will get a reductive group. Then you use this reductive to construct a reductive GIT. So PV is just the parametric space of these monomials, and T is just the two-dimensional torus. Then this space will provide a partial compactification for this space for our moduli space of the Pezzo pairs. Actually, you can also use the double covering construction to give a period point for these pairs. So according to the global Taylor theorem, you will get an open immersion. So P will be an open subset in the local niche metrical variety we introduced in last slide. So this space also has Baily-Borel compactifications. Of course, the K-moduli space introduced before will also give you severe compactifications for this space, at least partially, because the priori we may do not know every stable pairs is a K-stable one, but later you will see that is actually true. Okay, before I introduce our results, we need to introduce two dividers on the locally symmetrical varieties. These two dividers have arithmetic origin, but in our concrete example, these concrete examples, you will see that they come from the degenerations of our surface. The first divider is with hyperelliptic divider. This is constructed by the double cover of P2 double cover of P2 blob and 1 point. But in this case, we require that this curve C to satisfy some geometric condition that is tangent to the -1 curve E. If you still remember that we in our construction of GIT, we have a condition that the plane state curve has generically rank 2 and the blow up point. Maybe we can return a little bit here. We require the rank is 2. If you allow rank 1, actually you will get this geometry. Then you can explicitly compute its Lazy group. This Lazy group will look like this. This L is just still the polarization. E1, E2 just come from the splitting of this curve because it's tangent to the branch knockers. So E will split into two curves. The second divider we call it unique divider. It parameterizes the paired points of some K3 surface obtained by the double cover of minimal resolution of blob of P114. If you're familiar with the degeneration of P2, you know that P114 is just a degeneration of P2. So blob of P114 at 1 point will give you a degeneration of P2 blob 1 point. Then you can also compute its Lazy group. It will look like this. Here, E prime is just the proper transform of your exceptional divider over P, and F prime is just the proper transform of exceptional curve and the quotient singularidity, and the HY prime is a proper transform of the line defined by the coordinate y equal to 0. Okay, now we can state our main results. First, we computed the walls for our moduli space of the K-moduli space of these Pezzo pairs. So we divide our walls in two types. WH means the walls come from the hyperelliptic dividers. The WU means the walls come from the unique dividers. Second, we prove that for C is more, this space is empty because you know actually you know that P2 blob 1 point is unstable. So if you use the interpretation of K stability, you know that for small ranges, all the pairs will be unstable. Second, we prove that if C is in the first ring after the first wall 1/14, then we can identify this K-moduli space to the GID quotient, as we discussed before. Then we also identify some developed contractions of this wall crossing. The first wall crossing is first developed contraction is the developed contraction obtained by bluff and this wall. You will get the biracial transform of hyperunique divisors, and then the second developed contractions you will get the second developed contraction is the unicular divide. You will get the unicular divisors. We also have a arithmetic stratification for these two for hyperunique divisors. This stratification is known as the Laza left locus. Actually, we get the results that this Laza left locus is the proper transform of at each walls. And similarly, for the unicular divisors, we also obtain a similar arithmetic stratification, and the strata are also biracial to the exceptional locus and the unicular walls. And, here is our tables of the walls from the hyperelliptic divisor. These tables describes the centers of each wall. So you will see that in this case, the walls are very regular. Their singularities are described at the bluff point here. Yeah. And also we get the walls for the from the hyperunique divisors. Okay. Next, let's introduce the so-called Hassett Keel Looijenga program for our locally symmetrical space. We define this scheme priori as the project of section rings of this Q-line bundle. Oh, by the way, as the locally symmetrical varieties are always Q factorial. So yeah, so each line bundle is a Q-line bundle. It can be extended to Q-line bundles on the Baily-Borel combination because the boundary of this combination is very small. So you will see these coefficients are particular choice. You will see later that when we choose this coefficient. Actually, such type of space was introduced by Laza and Algebraic in their work to try to give a period map, try to give a resolution of period maps from the GIT of quartic surface to the Baily-Borel computation. Our second result is that we can identify our K-moduli space as this scheme. So you can see it is projective variety law. Because a priori we do not know whether this second ring is finely generated. Actually, this isomorphism can be induced by the biracial period map. So under this identification, you will see that the wall crossing for this HKL models are very regular, just some integers. Yeah. Under this transformation, these integers look like this. Okay, let's give a sketch of the proofs of our main results. To prove our first main results, maybe return back a little bit. The first result is determine the K-moduli walls and give an explicit describing of this wall crossing of K-moduli space. So let's give the sketch. Our first step is to determine all the possible K semi-stable deteriorations. So if you let xd to be the deteriorations of the Pezzo surface of degree 8, then it is well known that the central fiber will have so-called T singularities at worst. Here, T singularity means that that is KLT singularities can be smoothed. Then we can use a very powerful tool from K-moduli theory, that is normalized volume. Using the local to global volume comparison, we have such an inequality in our case. So on the left-hand side is just the global volume. On the right-hand side is just the normalized volume. So if the normalized volume is large, it says that the scalarity is better. If the scalarity is better, then you can almost determine which kind of surface it is. So we use the index 1 covering trick. We prove that our surface has index smaller than 3. Actually, using this normalized volume analysis, you cannot rule out that index is smaller than 2. But luckily, we have some classification results for the Pezzo surface of index smaller than 3. This is the work of Looijenga and Fujita Yusutaka. In the index 3 case, we show that they are unstable for all the C, or the coefficient. Actually, in the index 3 case, this surface is obtained by some explicit describing of Borel F5 and 2 points, and then you contraction some exceptional curves, you will get this surface. Then we use their explicit describing to show that they are K unstable. So the remaining case is index smaller than 2 case. In this case, according to their classification results, there are only 2 possibilities. The first one is just the original surface P2 blah 1 point. The second is just blob of P114 and 1 point. Oh, here, the point P must be a smooth point. So after the first step, we actually know all the possibility of surface appeared in our K-moduli space. Then if you want to determine the walls, we need to use the local VGAT structure of K-moduli space. The local VGAT structure says that if a pair in the center of the wall crossing, it must has an action of one-dimensional torus. So we can use this one-dimensional torus to compute its beta invariant. So this beta invariant must vanish because it has this torus action. So the remaining task is just to compute the beta invariant obtained by one-dimensional torus. We actually explicitly compute this beta invariant for all the possible one-dimensional torus. For example, for some one-dimensional torus with some weight on P2, we compute this A function and S function and this. Actually, in this case, the beta invariant of this the Futaki character of this one-dimensional torus just corresponds to some beta invariant of dividers obtained by weighted blob with some weight. This weight comes from this weight of the weight of one-dimensional torus. So we get this formula and this formula. So the condition that this Futaki character vanish will implies that we have inequality of A function equal to S function. Then you can get all the possibility of A and B, and also the possible curves of C. This will give us the potential walls. But if you need to check these potential walls are real walls, then you will use the equivalent K-stability criteria to show that the potential wall is a real wall. Yeah. So after the first step and the second step, you will get all the walls. So you will finish the first part of our results. Let's return a little bit. Here you will get these numbers after the step 1 and step 2. Okay, let's continue. The last step is to run wall crossings. The first step is you need to determine the first wall. Actually, we to determine the first wall, we need to show that for C is small, then the degeneration, the only possibility of degeneration is P2 blob 1 point. That is, you need to show blob of P114 will appear later than 1/14, our first wall. Then you can use the arguments of Liu and Xu in their proof of K-moduli space of cubic threefold is isomorphic to GIT moduli space. Then you use their arguments, you can show our K-moduli space after the first wall is isomorphic to this GIT space. Then you can get an explicit word crossing describing by analysis of local VGT behaviors for each word. Because after first two steps, you have know what is the word and what is the curve in and each word. Okay. So this is the sketch of the proof of our first main results. Okay. Maybe let's move to the sketch of our second main results. The second our second result is to maybe we return a little bit. The second result says that we have isomorphism of two space. The first space is the K-moduli space. The second is the Hassett Keel Looijenga model. Actually, our first step is to need to use the emptiness of CM-Lie bundle. Let's recall that the CM-Lie bundle on our moduli space is just can be defined by push forward of some cycles over our universal family. Oh, maybe I'm sorry. There is a table that this size is not right. Here it should be minus. But we need to first consider the universal family of our pairs. It's near the log Calabi-Yau case, so we need to consider 1/2 minus x0 for x0 is more. Because in this case, we have biracial contraction map from the last wall to the other walls. Here C is arbitrary. So as the CM-Lie bundle is ample, so you can easily to say that the section ring is just isomorphic or K-moduli space, the section ring of this CM-Lie bundle. So the remaining task is just to determine what is the CM-Lie bundle in this particular case. So the proof is reduced to show that the CM-Lie bundle after pullback to these locally symmetrical varieties is proportional to this. Here, you need to use the biracial period map. The second step is to apply the interpretation formulas of CM-Lie bundles. Recall that we have a formula for this CM-Lie bundle. Here, C is arbitrary coefficient in the follow range. That is, C is bigger than 0 and smaller than 1/2. In this formula, the CM-Lie bundle at C is divided into two parts. The first is the Hodge-Lie bundle. The second is the CM-Lie bundle, and this coefficient. So it remains to determine what is this CM-Lie bundle and what is this CM-Lie bundle. Oh, sorry, this is Hodge-Lie bundle. The Hodge-Lie bundle here is just the Hodge-Lie bundle on the locally symmetrical variety. This Lie bundle, you can write it as the linear combination of these three dividers. the hyperinic divisor, unique divisor, and the Hodge lie bundle. Because the locally symmetrical variety has pk number 3, so its pk group is just generated by these 3 divisors. So we need to determine what is the coefficient for this lie bundle. Actually, this lie bundle, these coefficients are determined by 3 important words. The first word is that we know the K-moduli space is isomorphic to a global GIT quotient. The second word is just the Borel contraction where hyperinic divisors appear. The third word is the unique divisor appear. For simplicity, we denote this lie bundle as delta C. The first coefficient we can determine is the coefficient of this Hodge lie bundle. Because we have known that our moduli space is empty, so before the 1/14, this this lie bundle will have no global sections. Of course, its multiple has no global section because this is just a Q lie bundle. Then we know that this divisor and this divisor are birationally contractible. So the positivity are determined by the coefficient of this Hodge lie bundle. Hodge lie bundle is ample. So if you use this word, you will get the coefficient of Hodge lie bundle must be -4. So it remains to determine the remaining 2 coefficient. For the coefficient of hyperelliptic divisors, you just look at the wall crossing and the wall where hyperelliptic divisor appears. You can restrict our lie bundle, just the pore bank of CM lie bundle and hyperelliptic divisor. It will vanish. So you will get the coefficient of hyperelliptic divisor. Similar arguments will give you the unique divisor. The coefficient of unique divisor is 25. But we need to use important relation for these lie bundles after restriction on divisor. Actually, this is done by using the work of Borchardt on automorphic forms of locally symmetrical varieties. Their technique will give us the relations between the so-called Hegel divisors on locally symmetrical variety. In our case, it gives us this relation. Here, Hn is just nodal divisors. It parameterizes the Pezzo pairs with the curve has only 1 node, but the surface is smooth. Okay. Then after this, we finish the proof of our second main results. Okay. Maybe I give some remarks in the remaining time. The first remark is that if you consider a similar problem for higher dimensional log follow pairs, to find the walls of K-moduli space is seems very hard than dimension 2. But the arithmetic stratifications might be useful to predict the walls for the K-moduli space, especially the K-moduli space is related to our K3 surface. more ambitious is you can consider similar problem for Fallot varieties related to so-called hyperkähler varieties. But the drawback is that arithmetic stratification just gives the predictions. So usually you will need to combine also the techniques from the K-moduli side. The last remark is that it may be interesting to look at the behaviors for coefficient and 1/2 or bigger than 1/2. For our coefficient C bigger than 1/2 by the recent work of Alexeyev, Engel, and Hans' work, the pairs we consider, they have a so-called KSBA moduli space. This KSBA moduli space has a natural normalization. This normalization has arithmetic compactification. This is so-called theoretic compactification for locally symmetrical varieties. For C is equal to 1/2. That is log Calabi-Yau case. It is expected to have a good moduli series for log Calabi-Yau pairs to collect wall crossings from K-moduli side to KSBA side. Yeah. I think this is the end of my talk. Thank you for your attention.